All right, and you know well enough what's coming next, so we considered a point object before. Now we're going to consider an extended object. So that way we can find a relation for the magnification. So we're going to have a y and a y prime for the height of the object and the image respectively. So here's our drawing for this guy. Oops. So we're going to have a similar circle here. And we have optical axis, something like that, maybe a little bit lower, something like that. And we're going to have this point V. We're going to have C being here. And we'll consider the similar case of NB here and NA being less than NB out there. So this, the reason this is a common standard thing to go with is because this could very well be air and this very well be glass. That's the index of refraction case for air and glass, which is typical for like a lens or an optical eyepiece of some sort. All right, so now we're considering an extended object. So we're going to do an arrow, and it's going to come straight up here. So this is going to be our point P. We're going to call this top of the arrow point Q, like we have before, and the height of it is Y. All right, and then we have the object distance being from here to the vertex. And that's S. So then we're going to consider our usual rays. So we're going to ignore the one from the bottom here. We know that that's going to go straight through, right? I'll draw it, might as well, but that's just kind of implicit. What we really care about is from the top of the arrow here. So we're going to do two things. We're going to go to the vertex and see what happens there. So it's coming away, away, and it's finishing there. So what happens is, since it's hitting the vertex, but it's not hitting it direct on, so that means that it doesn't quite, go straight like this. It's going to refract, and it's going to refract something like this, right? And if you consider the normal, and this angle, and that angle, and the indices of refraction, and the law of refraction, you can convince yourself pretty easily that that is what it would look like. All right, and so then we're going to do our radius of curvature would be, I don't know, somewhere about there. And that means that this would be normal, right? And we'll consider another ray coming from the top of the arrow that goes straight through the center of curvature, right? And I guess I didn't need to draw what I had previously. Straight through the center of curvature. I guess my it's going to make it difficult. I should have made these a little bit longer. Let's see if I can just do that. All right. So drawing is less perfect on this one than it has been in the past. Boom, boom. All right, so which puts our image point right at this intersect, right? And also, if you're saying, well, this one doesn't intersect, well, that's because that's point P, the bottom of the arrow, and this is P prime, and this is point Q, the top of the arrow. So we have a situation like this, right? And the height of the arrow is going to be Y prime. And we have an image distance from the vertex to where that arrow is. Always with our ketchup and mustard here. All right, so then we're going to identify these angles. So this is going to be the angle of incidence, say theta A. And this is going to be the angle of refraction, theta B, right? And this guy, he could be right there, right? But we actually honestly don't even need him. But I'll leave him be where he is. All right, so that's our image here. And we have the same thing going on with sine rules, but there's one extra thing to consider, and that is that when we have an extended object, anything above the optical axis is positive, and anything below the optical axis is negative. So that means that indeed this object, the y value here is positive, and the y value here in the image is negative, right? So we're looking at that guy there, negative. All right, so we can write down some things looking at some triangles. So we have triangles PQV, PQV, that one. And we have P prime, Q prime, and V. P, Q prime, and V. There. All right. So if we look at these are right triangles, and if we look at the tangents of the angles that we've identified, tangent of theta A is going to be equal to y over s. And tangent of theta B is going to be equal to negative y prime over s prime. I didn't write that down. S prime. And we already identified from before, since it's on the same side as the outgoing rays, then it's also positive. So positive, positive, and this one also positive. All right, and then, as always, we have our law of refraction. So NA times sine theta A is equal to NB sine theta B. All right, so small angles. We're going to assume small angles again. What does that mean physically in this consideration? What it means is that the height of this arrow, this object, isn't very tall in relation to how big the radius of curvature is. So nothing really like I've drawn it. We're considering an arrow that's pretty small, so that we can assume a small ray approximation, right? So not exactly like my exaggerated picture, but we're considering small objects for right now. That creates that small angle. And so if we do assume small angle, then we can say that tangent theta is about equal to theta itself. And so therefore, we can write that and also that sine theta is about equal to theta itself, right? And so therefore, interesting thing that comes out is that tangent of theta is about equal to the sine of theta, because they're both about equal to theta, right? So that means we can relate some of these sines to these tangents just as easily, right? And that might help us kind of leap a step there. So we can write NB sine theta B over NA. So that's just solving for sine A there, is equal to y over s, because this sine of theta A is about equal to tangent theta A if we're using the small angle approximation. All right. So then we can say sine theta B is equal to y over s times NA over NB. That was no better. There. All right. And so then, therefore, we can relate this guy and that guy, because sine theta B, if we're using small angle approximation, is about equal to tangent theta B. So then we can say, putting this on the left side, y over s NA over NB is about equal to negative y prime over S prime. Right? And we know that what we would like to arrive at is a relationship for magnification, right? Which is y prime over y. But we want to arrive at that in terms of other things. So now we can do that. So now we can say that y prime over y is equal to negative NA S prime over NB S. And that is our expression for magnification, lateral magnification specifically. For a spherical refracting surface. All right. So yet again, both of the boxed-in relations, both this magnification one and also this, this object image radius of curvature and indices of refraction for both materials, both of those expressions apply both to concave and convex refracting surfaces. The only thing that you might have to consider and think through is that the signs might change, right? So the signs might change if you have the surface curving the other way, because the images formed might be the other way. And so they also apply regardless of index of refraction, n sub a, n sub b, whether one is larger than the other or the other way around, right? So you just have to think through the signs, but it would take very little effort to arrive at what they become. So now we're going to do this thing again where we take r going to infinity. And so r going to infinity, and do you remember what that assumes? Taking r going to infinity we're looking at this guy here again. So I'll write that expression down here. And what is it? NA over S plus NB over S prime is equal to NB minus NA over R. Let me verify that's right. Yes. All right, so those are our two relations, and we're going to now consider taking r goes to infinity, which means plane surface. Right? All right, so that way we can arrive at if there's any kind of magnification for when light refracts at a plane surface, right? And we might expect the answer already, but let's get a check. So if you go r goes to infinity, then you're left with NA over S plus NB over S prime is equal to 0. And that means that NA over S is equal to negative NB over S prime, and therefore S prime is equal to negative NBS over NA. And if you plug this in to our, plug this in for S prime there, then you get that everything cancels out, including the negative sign. So that means that the magnification for when r goes to infinity, which is a plane surface, y prime over y turns into 1, right? No magnification, and the image is not inverted, right? Because the sign tells you whether the image is inverted or erect, and then the value tells you whether it's bigger or smaller than the object. So there's no magnification occurring when light refracts at a plane surface and the image is erect. So one thing before we close out this section that I'll share, and it's because the book mentioned it and I hadn't thought of it, and I love gardening. Let me copy over these images here. Let's see. Go to pages. Here we go. Oops, that's not where we are. We are here. There. All right, so take a quick sec for that to show up. There we go. So that flower is a flower that's in my garden, and it rained recently, And you can see that the little water droplets form spherical little beads on the flower. And those act as spherical refracting surfaces for light to go through. So light hits those, and it acts as a converging lens, and it makes all of the light hit at the same place that would have been spread out across the entire surface of, like the area of the bead. And so they always tell you to not water when it's really, really hot outside, because you can damage your plants. And I guess I didn't really consider why, but this is why. So this is what happens for this flower, at least. It's a very delicate little one. And you can see there's like little white spots going on, and that's because it's been damaged by too much sun being converged by previous water droplets hitting the different parts of the flower, and it just like burnt the color out of it. And so you can tell why, because now we have all the optics to consider of all the light coming in converges at a single point, P prime. And so instead of the light being nice and spread out across this, this whole area here, if you think of it as 3D as well, you get much more rays. They're all converging at a single point, and it's not a pinpoint because all the rays coming in aren't small angles. So it's this kind of blurred, dotted line or image that appears and ends up burning out the color on the flower. So there's a direct application to everything that we've been talking about right there in my garden, and I just had to share a picture of that. So when you water your plants, if you want happy plants, just water them in the evening or the morning, and it's tempting to think, oh, it's so hot outside, I bet these flowers want water. Well, they might, but just make sure you water the dirt and don't just spray misty drops all over, because you could be creating these little lenses and just like sending pins and needle burnt spots all over your plant. And the more delicate ones will certainly feel it. All right, that's that.